Live. We are live, and I somehow look exceedingly blue.
Maybe it's just compared to me.
No, I adjusted my colors, and I apparently landed on blue. Let's try and. Whoa, I just made you green. That was not the right button.
There
Let me.
are no green Frasers.
No, that's true. So, did you have a good New Year's, or at least a good enough New Year's?
I had a non-existent New Year's. like time passed, but
Mm-hmm.
I went to bed at 9, woke up the next morning, I'm like, it's 2023. Neat. So so we man, I'm so non-nostalgic about this kind of thing. Like Christmas even. Like we just don't care. And now that we don't have kids living in the house, we don't have to, right? Like we can
Exactly.
throw off all pretenses and just live our lives like
I like it.
normal. Yeah. We have one uh tradition, which is that we make these egg McMuffins, homemade egg McMuffins for
Ooh,
on Christmas morning. So we
I
make
like that.
those, and it was my aunt's. Apparently my mic is a little hot, but that's a you problem, not
Oh, I
me.
can fix that. Yeah.
Yeah, my aunt made these. Her name was Anne, so we called them Anne McMuffins, and so my cousin and I send messages back and forth of the muffins that we ate. But anyway, my point being, yeah,
That
no,
is
like
excellent.
maybe I'll come back around into it, but you do the parents in the audience will know you do 20 years of of organizing family get-togethers, of shopping, of wrapping, of getting a tree set up, and you just go, I no longer care. Like I have
Yeah.
zero. I call a bunch of friends and family on Christmas Day, but apart from that, no, it's all gone. Um, and the weather's been snowy. We're once again locked out of our road, so I have
Oh
to walk up and
no.
down carrying, you know,
Do
crates
you
full
have
of
like
groceries.
do you keep your car like
Yeah,
parked
yeah. We
down
keep the car
lower?
parked out, and yeah, we keep the car parked in a place that's accessible. So it's what's a lot easier. Um, and like we could get the road plowed, but it's like $300 each time you do it. Like maybe I could buy a
Yeah.
tractor. I could get one of those quads with a snow plow, or I could just leave the car parked down there and just walk down and grab it. And it's an extra 5 minutes on my trip, and
I
so I'm like, it's fine.
it's one of these things where depending on how climate change affects your weather,
Hmm.
either it makes zero sense or all the sense in the world to get that tractor with a plow on it, and you don't know yet. You
Yeah,
haven't
yeah.
lived there long enough.
There are other purposes that a guy could use a tractor for on a big chunk of land. So
That's true.
right, so I think a tractor is kind of inevitable, but I really don't want to get like a diesel tractor. So I
Yeah.
kind of we're looking at like electric tractors, but then they're first generation. They're probably suck. They're super
Yeah.
expensive. So I'm sort of biding my time right now, and I have other priorities. Like
Yeah.
I would rather I'd rather get an irrigation system installed and so on. So anyway,
Yeah.
that's my life. Um, and you, how was Disney?
Disney, we got really wet. So it was one of these things where I told everyone it's Florida in December. There's a reason the lines are shorter because it's Florida in December. So
Yeah,
bring rain gear.
yeah. The coldest day I ever experienced was winter
Summer
in
in San
winter.
Francisco.
No, winter in Orlando. It was cold
Yeah, well, it's
and
just such high
rainy.
humidity and it turned out that like folks were not prepared, but this led to the funniest thing I've seen at Disney. Everyone got completely soaked at Magic Kingdom. I'm talking like the entire park of humans got completely soaked. And so
Yeah,
folks were trying to figure out what they could buy to like completely change. And it turned out pajamas were the most cost effective thing to purchase. So by the end of the day, I'd say about 20% of the people at the park were just in pajamas. It was excellent. I
that's
thoroughly enjoyed it.
hilarious. That is awesome. Oh my god, that is so great to see. Like got to be some kind of sociological study here that could be made that like people are doing this cost benefit analysis. They didn't prepare. They wore the wrong clothes. Now they're wet. Are they willing to walk around in dry clothes that happen to be pajamas because pajamas are what's the cheapest? I love it. That is so great.
I figured like the first couple of people did it, or more likely the first few parents forced their children to do it.
Yeah.
And then it was just trickle down from there.
At that point. Yeah. I love it. That's so great. Oh my God. All right. Let's get into this this show.
Okay. I am looking for the record button on my audio. Hello. It is recording.
Okay.
I'm pressing the record on the video. We are recording everywhere, and I don't think I broke anything.
Oh, good. For once. All right. Astronomy Cast, episode 664, The First Stars. Welcome to Astronomy Cast, our weekly facts-based journey through the cosmos, where we help you understand not only what we know, but how we know what we know. I'm Fraser Cain. I'm the publisher of Universe Today. With me is Dr. Pamela, a senior scientist for the Planetary Science Institute and the director of CosmoQuest. Hey, Pamela, how you doing?
I am doing well. How are you doing?
Good. So we did a wrap-up of the space news in 2022. And while 2022, like many years, sucked, for space, it was the best. Right? We had Artemis. We had the James Webb Space Telescope. We had DART. We had the Chinese space station. We had so many amazing things come together. It feels like it was probably one of the best years in space in my career. So it's amazing. It was an amazing year. And I don't see as many exciting things coming up for 2023, but
that is true.
Who knows?
I see. I'm still mourning InSight. The InSight mission on Mars was my favorite little rover because of how hard that engineering team worked. It didn't rove. It just sat. It was my favorite little Mars sitter lander.
But it lasted twice its lifetime.
It did. And so I guess I'm still mourning. The little lander that tried so hard.
Well, like what more could you have asked for it?
A giant
should have lasted
earthquake.
For 4 times as long, 10 times as long. They can't all be opportunity.
I know.
Right. All right. The sun is a third-generation star, polluted with the metals from long-dead suns. Astronomers have also discovered second-generation stars with very low metallicity, but theories suggest there must be a first generation with stars made from only pure hydrogen and helium. Can we ever find them? And we'll talk about it in a second, but it's time for a break. And we're back. So first, please explain the generation numbering scheme for stars, because it's ridiculous.
Okay.
We live in a pop. We have a pop 1 star.
Yeah.
And there are 2 stars.
Astronomers shouldn't be allowed to name things or set the directions of calibrations, and I'm going to sneeze. All right. So continuing on. So just like astronomers screwed up in terms of calling like the brightest stars magnitude 0, meaning faint stars are magnitude 20, we decided that our current population is number 1. We're number 1.
Right. Because we're the first star that we ever discovered.
Well, yeah, we are the first star we ever discovered. Sort of, I guess. You fell asleep the first night and then you found all the rest of them. Yeah. But anyways, so the generation of stars older than us that doesn't have as many metals, can't probably form planets the same way, those are population 2. And as illogical as it can possibly be, the first generation of stars the universe ever formed is population 3.
Right. So it makes sense. The first star that we ever discovered, they're population 1. The second stars that we ever discovered, those are population 2. And then we're hoping someday we'll find the third stars, the type of stars, which will be population 3. Still theorized. Okay, so that is and then how do you define them? Like as an astronomer, when do you take a star and put it into the pop 1 bucket and put it into the pop 2 bucket and the theoretical pop 3 bucket?
So pop 3 means these stars are primordial ingredients. They are made of the exact same stuff that was produced in the Big Bang. Hydrogen, helium, maybe a trace amount of lithium and beryllium. Definitely a trace amount of lithium and beryllium. But then pop 1 are all the stars like our sun that are being formed currently. These are things that are 2 to 3% of atoms heavier than hydrogen and helium, and the stuff in between is the population 2. So once you start getting to the point, and I'm sure this is going to get redefined as the formation of planets plays a larger and larger role, but pretty much once you start getting to the point that you're not seeing planets forming, that's where you have population 2 stars.
Although I'm sure someone's found planets around pop 2 stars or will shortly. Like
the issue is population 2 stars. These are objects that are generally less than 1% of heavier atoms, and if you don't have heavier atoms, you can't form planets. So one of the amazing things is globular clusters out there. These are population 2 stars orbiting our galaxy. They don't have planets so far, and we have looked as hard as we can possibly look at things that far away, and they're just not showing up.
So there's one known type 2 star that has a planet.
Are we sure?
Well, it's called Captain Star. It's a M1 red subdwarf, and the metallicity is about 14% of the sun, which classifies it in the type 2 star.
How do you always find these exceptions?
Because I have a hunt. Like here's my standard operating procedure, right? Is that I think all I do is report on surprising new discoveries and new things moving forward. And so like it feels like somewhere there is a headline, astronomers find the first planet around a type 2 star. And like, yeah. Anyway, and I'm sure they'll find many more because, astronomers shocked to discover theories overturned. So yeah. All right, we're going to talk more about the first stars in a second, which we know we don't know of any.
It's true. We don't yet.
We'll be back in a second. Well, wait a second. I may have news for you then. We'll be back in a second. And we're back. All right, so we've classified the pop 1 star, the pop 2 star. Let's talk about the pop 3. So these are theoretical, as you say. They are made of the pristine material left over from the Big Bang, pure hydrogen and helium are the exact constituents left over when the universe had cooled down that these atoms could form. How would they be different from a star like we have today? I'm going to guess no planets, but then even that, like, I'm sure some people are going to be like, we found planets around, we discovered pop 3 stars, and we also discovered a planet, a gas giant. Who knows?
All right. So
pop 3 gas giants. Anyway, please continue.
All right.
What would they be like?
So one of the weirdest things in trying to understand stars is what are the effects that those heavier elements have on the ability of the star to form and radiate heat. And it turns out that if a star is made of pretty much just hydrogen and helium, the light that is forming in its core just radiates out. And because it's radiating away and not interacting as much with the protons and electrons, because the energy levels just aren't right, the star is able to become much more massive before it starts pushing out its outer layers. And a star that's more massive, in this case 100 to 300 times the mass of our sun, it's only going to live for 1 million-ish years. So we're in the situation where the very first stars formed roughly 100 million years after our universe formed. And then they only lived for 1,000,000 years before they underwent this super weird form of supernovae where the star essentially eats itself from the inside out and leaves nothing behind except for a spray of light and heavier elements.
So you don't get a black hole, you don't get a neutron star, you just get the thing detonating completely.
It's called a para-instability supernovae. And
so talk about this. You say eats itself from the inside. What is actually happening with para instability?
So you have in the core of the star, gamma ray photons are getting produced. And these extremely high energy gamma ray photons, they're going to be interacting with protons, with electrons, not as efficiently as if there were metals. And they're also going to be interacting with each other. And ideally, the rate of energy production is such that the star is in thermodynamical equilibrium. Gravity is pushing inwards, heat and light are pushing outwards. Again, the light isn't as effective here because it's mostly just flying through the atoms. And when these gamma rays interact with each other, they will produce an electron and a positron. This is a particle and an antiparticle that are able to then later interact with each other if they hit each other later and produce more gamma rays. But because of the kinetic energies involved, some of the energy is lost in this process. And the lower energy gamma rays are going to lead to a changing situation where the outer layer of the star isn't being supported as well. The star begins to collapse down. As the star collapses down, it heats up. More gamma rays are produced. Gamma rays interact with each other because there's more of them. It's easier for them to interact. They produce more positrons and electrons. These interact and annihilate. And the star is literally eating itself out of having matter and energy through the loss of energy to kinetic energy. It's wild. And what gets me is we think we may have actually been able to see the chemical fingerprint of one of these kinds of supernovae in the light of distant quasars.
Okay, well, that was the evidence I was going to bring up. So then, yeah. And so, I mean, we see those para instability supernovae. We've seen these detonations before, but just from heavier stars, just stars with other elements like POP2 or POP3, POP1. Sorry, I got to get this straight. But second, third generation stars, but they're very massive. They have exploded as para instability supernovae and just completely vaporized themselves. No black hole, no neutron star, just kablooey.
Yeah.
Okay. All right. So they live past. Now you were starting to make some estimates of their masses: 100 times the mass of the sun, 200 times the mass of the sun. Do we have a sense of how big these things can get?
This is where you end up with a lot of different people arguing in the literature. There are some folks that are like, above 300 solar masses, the energy being produced is going to cause no additional material to be able to fall onto the star. It's going to be quenched. There are those that are like, at 150 solar masses, that's going to happen. There are those who are like, at 1,000 solar masses, that's going to happen. The safe bet is it's occurring in the hundreds of solar mass range because, as you pointed out, we do see some massive stars in our modern universe. These are objects that are 150 solar mass to 200 solar mass when they first form, and they do have these para instability supernovae when they die. So just how big the very first ones get, we're looking at hundreds as a safe bet, but exactly how many hundreds, we're not sure.
And there could be all kinds of weird dynamics that are going on. There could be magnetic field lines, there could be accretion disks, there could be ways to get beyond pushing that material back away from the star. And that's why it's like, I saw a simulation where they thought that maybe you could get into the tens of thousands of times the mass of the sun. Like, crazy. And then, like, what a they simulated in a supercomputer what a supernova would look like when a 50,000 solar mass star goes through this para instability process.
And then that light doesn't get very far because the early universe was not yet ionized again,
Right.
reionized. So all of this is going on behind opaque layers of gas hiding from us.
Huh.
So
Like we think about the cosmic microwave background as this, like someone came and turned off a switch, but it wasn't like that.
no.
It was this long, slow, gradual process of the clouds lifting over the course of several millions of years. And so could you have had these first generation stars forming within this fog of the early universe?
Yes, that's exactly where they would have been forming. And we're starting through gravitationally lensed galaxies to be able to see the age of reionization, to see early galaxies that still have these clouds of neutral gas around them. But the very first generation, the closest we can come to hoping to be able to find them is that there are pockets of gas out there that just somehow got isolated and left alone for the fullness of time. And there's one AGC 198691. I have to look at its license plate number. It is 1/20% made of atoms heavier than helium, and it has 1/40 the metallicity of our sun, which means it has population 2 stars. But it is so metal poor that it starts to give us hope that maybe we'll get lucky, and while there's not anything in the nearby universe that is pristine material just starting to form stars, maybe we're going to be able to find some lensed system from the first billion years of the universe that we're able to start catching the light of those first supernovae.
All right, we're going to talk about this some more in a second, but it's time for another break. And we're back. So then I guess I got two questions. I got to remember to bring up the other thing before we end the show. But anyway, so first let's talk about trying to observe them. So you mentioned that, like, even though these stars are ludicrously bright, even though their supernova are brighter probably than any supernova we've ever seen, they are cloaked in the fog of the early universe and will be difficult to see.
Yes.
Both their existence, but also their death. How could we theoretically see them?
If they formed in a pristine galaxy or a pristine blob of gas that managed to escape the first round of star formation, like a blob of cookie dough without chocolate chips that escaped onto the counter. That escaped gas is probably the best hope we have of seeing these things. Now, the other problem that we're dealing with is, if you go back to some of the earliest episodes of the show, we talked about the missing G dwarf problem. This idea that low mass stars have the capacity to live longer than our universe has been around. So the very first lower mass stars to form should still be out there shining. Mm-hmm. And this is where we get ourselves into trouble of just how effective was the mixing and how much metal does it take to start forming lower mass stars. And these are things we're still trying to figure out. So on one side, you have people looking for the oldest low mass stars that were the very first low mass stars to have ever formed. And on the other side, you have people trying to find pristine pockets of gas in dwarf irregular galaxies, in other forms of dwarf galaxies that just don't have anything to increase the mass of stars as they form, increase the metallicity of stars as they form.
Right. Now you mentioned like maybe through lensing. So
yes.
Hubble never could, but no. I know that using gravitational lenses in the way that Hubble could see the farthest galaxies, Webb could be able to see the farthest stars.
And this is where, at the time that we're recording this, we are about a week and a half away from getting the first deluge of science to come from the JWST at the American Astronomical
Oh,
Society
it's AAS meeting. Oh yeah, I never even thought about that. You're right. It's just going to be chock-a-block, isn't it?
They're going to have a whole lot of early results from JWST being announced. And I'm kind of afraid that anything I say other than JWST was specifically built with finding first stars in mind is going to be out of date within weeks of this episode going live. So stay tuned.
We should
we're
maybe
4
do
weeks
an
away.
episode.
We have
Yeah,
it
you know what?
scheduled.
Let's do an episode. Or it's already scheduled? Okay.
Yeah,
all right. Yeah. We'll do a first science result, first proper science announcements from JWST. That sounds great. So what would it take then to build? What kind of instrument could see them directly? Because I know there was a space telescope, the Origin Space Telescope, that was shelved, and that was going to be a 9 to 12 meter class infrared observatory, essentially a super duper version of JWST. That was hoped could maybe find evidence of the pop 3 stars.
Right. So what we need is something that is capable of seeing the faintest light from dwarf galaxies that are being gravitationally lensed, or from galaxies that aren't yet fully fledged, fully full of light. This goes back to how do galaxies form. We have this notion today that they form both through the massive collapse of giant pockets of gas, but also through smaller pockets that collapse into dwarf systems and then merge together. Those dwarf systems that have less mass in them will form stars at a slower rate. Big things form faster, small things form slower. By being able to see dwarf systems that are being gravitationally lensed and are super faint and are in the earliest days of the universe, so their light is redshifted into the infrared, we can get back about as far as we can get back.
Right.
It's hard. It's hard.
Yeah. Now, when you think about the size of these stars, and we talked about how they don't seem to form, they probably don't form black holes, but there's got to be some kind of link. Could there be some kind of link between these first generation stars and the supermassive black holes, which are also a mystery because they don't seem to be able to form quickly enough to have the mass that they have already in the universe that we see them? Is there some connection between these first generation stars and these monster black holes?
At a certain level, yes, because you're again at this problem of if you have an atom like technetium is my own personal enemy, because in stellar spectrum, technetium, it has electrons bouncing around at all the interesting, visibly apparent in your standard optical telescope colors of light. So you're trying to study whatever small magnesium hydride was what I was working on, whatever small molecular lines or atomic lines. And technetium is there going, hi, there's a few atoms of me. We're going to dominate everything. And what's happening is as the energy tries to radiate out from the center of the star, it's absorbed in by all these different energy levels of the electrons in the technetium and then re-radiated as the electrons jump between energy levels going back down. So you have this 1-2 whammy of a whole lot more electrons involved in the energy levels and a whole lot more energy levels that increases the ability to re-radiate that energy. And this causes a pressure, essentially. So the light goes out, it gets absorbed into these atoms, and that supports the outer layer of the star. If you don't have all these energy levels to absorb in the protons just fly through. So this allows giant stars to form. Well, if you're in an early galaxy and you have collapsing mass that is able to heat up and much more effectively radiate out energy, you can first of all get bigger that way. And then models that look at adding in turbulence to again allow more mass to get down in there than you could through a nice calm collapse. This 1-2 punch of lower metallicity and significant turbulence allows you to start getting at supermassive black holes. Maybe.
Right. There's an interesting experiment you can do talking about turbulence. You can take a bottle of pop, what you may call soda, and you turn it upside down and it glugs out and it's very slow. But if you give it a spin, then the water pours out because it gets an air hole coming up the middle of this vortex, and the thing will just empty in a heartbeat.
Yeah.
Just boom, completely empty. And so turbulence can have a tremendous effect. So when one idea, if the turbulence models are right, is and if they do just keep gaining mass forever, is you don't get the parent stability supernova. Instead, you just get this direct collapse into a supermassive black hole.
Yeah.
That would be crazy. That's amazing. Yeah, to think that however many million times the mass of the sun could all collect together into one spot and then just directly turn into a black hole.
And it all comes down to how big were the slight overdensities and underdensities of mass in the early universe. If we had had a different distribution of overdensities, we might have become a universe of nothing but supermassive black holes. So there's your food for thought for the day.
I love it. All right. Well, that was fantastic, Pamela. Thank you so much.
Thank you. And thank you to all of our patrons out there. We wouldn't be here without you. And this week, I want to thank Brian Cagle, David Everson, Bruno Letts, Alex Rain. And I'm going to pause and say, we now have an ad-free distribution of this show on an RS feed through Patreon that you can only get if you're a Patreon. So I'm going to keep going. We're thanking Michael Perjata, Burry Gowen, Stephen Veit, Gordon Young, Jeanette Wink, Kevin Lyle, Nano Flips, Bara Andre Livsval, JF Rajat, Venkatesh Chary, Andrew Poelstra, Brian Cagle, David Truog, Aurora Lipper, David, Gerhard Schwarzer, Buzz Parsec, Coco Sarif, Laura Kettleson, Robert Plasma, Jack Mudge, Les Howard, Joe Holstein, Frank Tippin, Gordon Dewis, Alexis, Adam Anise Brown, Richard Drum, William Backer, Wanderer M101, Zero Chill, Felix Goot, Andrew Setz, our Astro Setz, William Andrews Gold, Roland Vormerdam, Jeff Collins, Simon Parton, Kellyanne and David Parker, Jeremy Kerwin, Rob Cuff, Harold Bardenhagen, Matthew Horstman, Alex Cohen, Philip Walker, Marco Iarasi, David Gates, Scott Cohn, Scott Bieber, Justin Proctor, Matthias Hayden, Claudia Mastriani, Kensaya Pinflienko, Daniel Loosely, Jim Schooler, Gregory Singleton, Disastrina Cooper, Tim Garish, Tim McMacken, Jeff Wilson, Paul D. Disney, Aaron Zegrev, Ninja Nick, Kenneth Ryan. And don't you love that there's fewer episodes in January and there's that many more names at the end of the episode?
Fantastic. Thank you, everyone, for supporting the work that we do. And we will see all of you next week.
Bye-bye, everyone. And then they saved.
And then they saved. And then hit us with your questions, or you will get a rant.
This is true.
Because that works. That's how it plays. Although maybe people are baiting me into doing a rant, so I don't know. Maybe that's what it is. They're holding their questions because they want a rant.
All right, let's see what all we have.
Upload.
Thank you for the sub, Real Fake Admin over on Twitch. Thank you.
Okay, Quadlibit asks, other than giving us some heavy elements and maybe anchor points to forming galaxies, what did the first stars ever do for us? What is the non-stick frying pan justification to find them?
First of all, I want to say to Freya's Fury PhD, this is not old. We are not airing a repeat. This is live, my human.
This is live.
All right. So, I mean, sometimes in astronomy, we just want to find things to answer fundamental questions like, how did we get here?
They also were the factories for all of the elements in the universe.
Yeah,
so
which is
thank
how
you.
we got here.
What have they done for us? They gave us
got us
everything.
here.
Yeah, and they asked for nothing. They gave of themselves. Sacrifice.
Cantab is asking live on what date. It is January 2nd.
Ooh.
But
or the artificial intelligence routine that we're running was able to fake that.
The episode will air on January 9th.
James Robert asks, how do we measure the magnetic field strength of distant objects like neutron stars and magnetars?
We look at what's called Zeeman line splitting is one way that we do it. So there is a difference in the energy between a spin up and a spin down electron, and that difference in energy gets more apparent the higher the magnetic field is. So when you have electrons jumping between energy levels, you'll actually get this splitting in the lines between the two electrons in a given energy level under high magnetic fields that it's possible to see.
And then you get the radiation coming from this jumping, and the wavelength tells you the magnetic strength.
There's also effects on polarity of how light is reflected off of dust, because you can get dust aligning. There's lots of cool ways, but my favorite is that Zeeman line splitting, just because this is something we can calculate and then we see it in the universe. And I'm a fan of things that the math says and the universe says, and they match.
That's the perfect, that's what you're hoping for.
Yes.
If you're a theorist and you have ideas, then
string theory does not make predictions. I do not. Right. I'm not a fan.
Sure. So you make your predictions. Your math makes a bunch of testable hypotheses, and then people test those hypotheses, and they are able to either confirm or deny them. That is science in its purest form. Janelle Duncan asks, are you planning anything special for a sample return from Bennu?
That's coming up in September. Yes, but I don't know what yet. The world
there'll
is
be
still weird.
Yeah, what did we learn from Bennu? I'm sure there will be an episode where
there's also just going to be a watching it come in and either doing something like a celebration in Discord or a celebration on one of the live streaming platforms. Yes.
But I can imagine an episode on asteroid sample return, because we've got the Hayabusa missions and then we've got this one.
Yeah.
There's a lot of interesting information that's been discovered from Hayabusa, and you'll add that with Bennu. I think it'll be terrific. Yeah.
Mid 2024.
Is that when you think they will have done their science?
Research papers, to do a good review.
We saw some stuff within a couple of months, some early results and stuff within a couple of months after Hayabusa 2 returned.
See, I'm thinking LPSC 2024 is when we're going to get a full session of Bennu results.
There you go, Janelle. So we'll do something special in about a year and a half.
Mike Castee is like, Bennu is my friend. I love Bennu.
Oh, there's a whole group of people who hate that rock.
You can love-hate something.
Yeah. Who think that DART should have been slammed into Bennu instead, just to teach it a lesson.
The problem is it would have gone through Bennu, I think. That would have been a bad day for everything.
Ben
I
Cagle
love
asks,
that there's still an observable tail from DART.
Ben Cagle asks, any thoughts on XKCD's announcement of the L6 Lagrange point? Yeah, I loved that. It was so good.
I didn't see that.
A 6 Lagrange point has been found on Earth. It's so good.
This is me Googling.
Yeah. XKCD L6 Lagrange point.
Okay, fair enough.
Yeah, that's so good. Yeah. It's just outside of Cleveland.
Yes.
It's difficult to shift orbit L6 stably due to the gravitational perturbation from Akron and Toledo. Okay, hold on. James Stark asks, how do you distinguish different types of supernovae in distant galaxies?
It's a combination of what are the atoms that are emitting light, what is the rise and fall shape and time, and those are really the two big things we look for, is what's it made of and how does its light rise and fall.
Quadlibet asks, is it possible there may be pockets of pure hydrogen out there that are big enough to create an approximation of a first star in the present or maybe in the future?
Yes.
Yeah, okay. So why?
So we can very easily find the largest overdensities in the early universe because they have formed the largest superclusters of galaxies in the modern universe. For every supercluster, there had to be a super empty spot. And so there is the potential that through some fluke of the shock waves shocked in just the right ways, the gravity pulled in just the right ways, that some little pocket managed to get left alone, holding itself together desperately, that will one day experience some sort of a disruption that does cause it to finally go, okay, I'm going to form stars. I'm going to do it
Right.
now.
So all of the star forming regions here in the Milky Way, they are made of most hydrogen and helium, but they're also polluted by these heavier elements. But there
Right.
would be just vast clouds out there that have never been hit, never polluted.
So we're looking for basically a dwarf galaxy's worth of mass. And this isn't to say that there's definitely some out there, but it's to say there's the possibility that they're out there.
John Cephal asks, if planets are formed from a disk of dust, how come the Oort cloud is a sphere?
I should know this. It's this problem of you have a collapsing mass and the kinematics of how things collapse causes disks to form. And then within the disk, you have things hitting each other that fling stuff in random amounts of directions. And I don't remember the full reason for how the Oort cloud ends up, whether it's purely leftovers or it's flungage. I just don't remember.
Or collected
Yeah.
from other star
How
systems?
did the...
Yeah.
I only pretend to be a planetary scientist on the internet. I'm really an astronomer.
Yeah.
Beth, if you're out there watching,
Beth can jump in with the answer on this one.
maybe if she's out there somewhere.
John Cephal asks, is there a theoretical fourth generation star after Pop 1? I guess before, like Pop 0. No, Pop 3. I guess after us. So will there be a future type of star that is even more metal rich?
And yes, we are already finding stars more metal rich. So the question becomes, at what point do you say, this is population 0, we've left the sun behind?
Right. It's a definition. But I guess you would need some kind of new behavior. So if there were stars that had the mass of the sun, but they were so metal polluted that for some reason they
couldn't
function,
form large stars anymore.
Yeah, or they had a different stellar characteristic or something,
Yeah.
then you might come up with a different classification for them. That'd be interesting. If you'd ever reach that point where a star changed dramatically because it was too polluted by stuff. Like people always say, wonder if iron is poison to stars. And it's not. I mean, it's the point at which the fusion process ends, but you could feed a star iron and you would eventually just dilute its ability to create fusion in the core. It's not like it's going to kill the star.
And we find stars all the time that have an outer shell that shows that they ate something. Mm-hmm. They either went through the remnants of another star or they sucked material off of another star.
Or they ate planets.
Yeah, and so they have this enriched shell that is giving off those characteristic emission and absorption lines. You don't give off an absorption line; you highlight an absorption line. Um,
Right.
but
You
anyways,
you block an absorption line. I don't
yeah,
know what you
yeah.
call it. Yeah. Yeah, that's interesting. Rajaluthra asks, can scientists predict if a star at the end of its life will become a star again?
Um, Okay, so there are systems where there's multiple star systems where we see the mass going back and forth, or where two objects can come together and form a new star. These actually appear in annoying numbers in globular clusters and are called blue stragglers. It took ages to figure out what the heck was going on with those. And they are where basically a star gets a new lease on life, or a star is undead. I don't know what you want to
Yeah,
call them.
right.
Uh, they're kind of vampiric in nature, I guess. Um, but for a singleton star, their mass gets scattered out and forms how the materials for however many other stars out there.
So you would predict that a star is going to have a new lease on life when you watch it colliding with another star. That
Yeah.
would be your hint that something interesting is about to happen. Apart from that, stars follow this very straightforward process from life to death.
Yeah, one stupid way to think about it is I eat bread products because bread is tasty, and then I exhale carbon dioxide that then gets, in the fullness of time and scattering, reabsorbed into new wheat plants to form new bagels. So essentially, the bagels of the past are helping to form the bagels of the future via the carbon cycle.
Right.
Um,
Yeah, that's awesome. I mean, people always have that. They say like you are some of your atoms were once in every famous person you could think of.
in their lungs, yeah.
Just in the carbon that forms your
Yeah.
body was probably a few atoms come from almost every famous human being that's ever lived. All hail the time bagels, says Gordon. Um, James Stark asks, how do you know that some material is in the shell of a star rather than part of the star?
Well, being in the shell is still being part of the star, but
Yeah.
it comes down to the outer layers of a star are a different temperature, and the outer temperature corresponds to the atoms we see in the outer part of the star. And there's just certain stuff that shouldn't exist on the outside of a star. A whole bunch of carbon should not exist on the outside of a star. So when we see things like that, and stars are opaque, we can't see down into their cores, that tells us that the star ate something that was rich in carbon, like a bagel.
Deepak Singh asks, have we detected the candidates of the earliest galaxies or a baby galaxy?
Yes, the one that I named, AGC 198691. It's one of those dwarf irregulars in our modern galaxy that hasn't been very enriched, and we are seeing the first massive stars being lensed. The trick now is to go from finding nearby dwarf irregulars and faraway massive stars, massive galaxies, to finding faraway dwarf irregulars.
Um, and Raj Lutha asks, would we have any idea what new technologies, hypotheses, and techniques would be created from searching for these first stars? Any new
Better,
technology? Can we get any
cheaper
technology?
infrared cameras. I mean,
Right, right. Better cooling for infrared cameras in space?
it's, you never know where innovation is going to come
Yeah.
from. Uh, Wi-Fi exists from radio astronomers trying to get their signals to be more clear. Uh, CCD technology, which has led to the CMOS chips in all of our phones, was developed for astronomy, but at the same time, there's been so many military techniques like adaptive optics that have been stolen ruthlessly for astronomy. There's processing techniques that come from medical imaging that get used to get the smallest details out of astronomical images. No knowledge is useless. It's just sometimes waiting to have a use be found.
My favorite kinds of stories, the ones that I try to zero in on when we're doing reporting on Universe Today, is those kinds of stories where somebody thought it was impossible to be able to image this kind of thing, and then someone had a clever insight using this other technology and brought that over to be able to use it. I think one of my favorite recent examples is in the LIGO, in the they developed a technique called quantum squeezing.
Yeah.
And so you know that you can either know the position or the motion of a particle, but you can't know both at the same time, right? This is the uncertainty principle. But what they found is that you can squeeze one of those factors and make the other one even less known, but give you more accuracy on the other one.
Yeah.
And they were able to use that technique. It was developed in something else, optics or whatever, and they were able to use it in LIGO because they don't care about the motion, but they want the accuracy of the photons, I think.
Yeah.
I forget which one it was. And so they squeeze the uncertainty out so that it is pushed in the direction that they need. And they were able to get the level of accuracy with LIGO to be able to now make observations, gravitational wave observatory observations, once a week as opposed to once a year.
And this is
amazing.
where people talking to each other and social media becomes so important, because you never know who has information that they are using for this thing over here that you can use for what you're doing. One of my favorite cases of this was Jordan Steckloff, who is a planetary scientist, wrote code for figuring out how comets of various compositions get melted as they come closer to stars. Well, if comets are objects that are a combination of various ices and minerals, and asteroids are objects that are composed of minerals and various ices, at a certain point, you're going to have asteroids that you can now see, well, what kind of a star can I destroy an asteroid on? And he was able to figure out that your youngest, hottest white dwarf stars you can't put asteroids right next to, because they will vaporize the asteroids the same way our sun vaporizes your standard comet.
That's really interesting.
So stick a planetary scientist at a table with astronomers with the right questions, and you can destroy a planet.
And I mean, that process of people from disparate fields sharing their problems, but being creative about each other's, work, creates these wonderful new techniques and technologies and so on. It's so great. Like, one of my favorite things to do when I'm interviewing somebody is I hear about the challenges they're facing, and I'll bring up other people who are working on similar stuff in different fields. And in many cases, they because you can't, like, I think our assumption is that scientists are on top of everything, but they're just people, and they're trying to get through. They have to grade. Yeah, they can only read so many papers. I'll say, like, I read this paper, I read that paper, and they're like, I haven't read those papers yet, right? So this stuff finds their way to them eventually, but it's just great. And that those insights that come cross field, like, I wish, like, if there's one thing artificial intelligence could do for us, is bring together those insights from across fields, because there are hundreds of thousands of papers that are published on journals every year. Imagine, and no one has time to look through them all, but imagine if you're working on something and the AI taps you on the shoulder and says, by the way, did you know that some biologists working with ant colonies have figured out a way to blah, blah, blah. And you're like, that's exactly what I need. So that will be terrific if we can get some more of that. We've reached almost the end of our hour, so I want to give a chance to find out what you're working on. What can people expect now that you're back in the captain's chair?
So right now we're doing, I hate saying this, we're doing a fundraising push because you and I, we don't get paid to do Astronomy Cast. We do pay our staff really well to make sure everything's well produced, and you earn your living through Universe Today. And I should be earning my living through CosmoQuest, where I spend most of my time, but I've actually been earning it through side hustles. And one of our staff members, Ali Pelfrey, did the internet version of hitting me with a newspaper and said, "Stop that. We're going to raise money so that you can pay yourself." So, yeah, join the Patreon for CosmoQuest if you want to see me paid. We do have a small grant that we're going to be working on a new lunar citizen science project. The Real Fake Admin, who I mentioned earlier over on Twitch, he's been working on the software for our citizen science projects with us, and we're working on making real progress on our redesign. And yeah, I'm going to be focusing on citizen science once I don't have to side hustle so hard.
Yeah, I don't think people realize that, we've been doing this job for 15 years. We've produced 660 plus episodes. We don't take any salary from this at all. But all of the Patreon, all the advertising revenue, that just goes to the team.
Yeah.
And if you want to support me, then go to patreon.com/universe today. And if you want to support Pamela, go to patreon.com/CosmoQuest. And that's how you support us directly as creators for the work that we do. For Pamela, creating this enormous citizen science empire, and on my side, all of the space news that we produce. I've got a couple of things happening. One is I've got a new interview coming out tomorrow with Adam Frank, Dr. Adam Frank, who's one of my favorite scientists / science communicators. And you're going to love this, Pamela. He has worked out a way to take an asteroid, a rubble pile asteroid like Bennu, surround it with a bag, spin it up, and you make a habitat, a torus. You make an O'Neill cylinder with no construction necessary.
I like it.
I know.
I like it.
So
it's hilarious.
They tried spinning regular asteroids and they can't hold.
Yeah, they fall apart.
And so, but this way,
you start with one that has already fallen apart.
You spin it up and you get this amazing bag, which is just of asteroid, which is just such a great idea. I love it.
One thing I always forget to say when I'm traveling, I'm going to go to my first science fiction fantasy convention since this stupid virus started. The Aresia convention in Boston. You have to have had your bivariant vaccine by tomorrow in order to be allowed to attend. It's all vaccines required, must be masked at all times, or they will boot your butt out the door. I'm going to be going and participating in my first ever art show as an artist.
That's great. I'm glad you're attending something.
Yes.
Don't get COVID. And then the other thing was I finished a book. I read. So I read Revelation Space by Alistair Reynolds, and a lot of people have been recommending this book at me. Have you read it?
I'm trying to figure out if I'm reading a book by Alistair Reynolds right now, and I don't know the name of the book because that's who I am as a person.
Okay.
I'm reading Blue Remembered Earth right now.
Okay. So phenomenal book. It is. It tickles the same feelings as Three Body Problem, but with really good characters as opposed to non-existent characters. So the ideas are the same scale as Three Body Problem, but also the characters are strong and interesting and very complicated. Yeah. It's a wonderful book. It feels like one of the best science fiction books I've ever read. So I'm so glad everybody kept recommending this book to me, and finally got around to it, and I just loved it. So Revelation Space by Alistair Reynolds.
We spinned up a new Minecraft server as a Christmas gift to the CosmoQuest community, And I'm not going to lie, I spent like 2 straight days listening to an audiobook and digging holes because
Diggy hole. Yeah,
yeah, diggy hole. That's what I do.
that's awesome. All right. Well, thank you everyone for joining us today. Welcome back to the Astronomy Cast. No more breaks through till summer. So, well, who knows? There might be a break.
Who's the
But
guest on Wednesday for Weekly Space Hangout?
I don't know.
Okay,
I have no idea.
continue on.
Yeah. And thank you everyone for hanging out. Thanks for the mods. I know you had a little work today. I was watching. Thank you everyone for watching us both on YouTube and on Twitch. And we will see all of you next week. Or tonight for my open space. Come join.
Okay.
All right.
Okay.
Thanks everyone. See you later.
Bye-bye.